Hi everyone, today starts our exploration of tangent, and we're going to get right into this conversation by first remembering what tangent means. Last night for homework you all explored actually calculating tangent as you made your way around the unit circle. So first of all, recalling sine and cosine, the ordered pair x, y, where x generated your cosine value, y was your sine value, and the value of tangent in that table came from calculating y divided by x, which, as we just said, is the same as sine of theta divided by cosine of theta. And we'll be using your table values in a couple minutes, but first, I'm hoping as you were doing these calculations, or even right now as I mention it, if I were to have asked you, where in algebra have you seen change in y divided by change in x, I'm hoping that we're thinking algebra 1, and you would be right. So really, when you're calculating y divided by x, you are actually finding a rate of change, or slope, whichever word you would like to use. Which is the change in y divided by the change in x. So really, as you're calculating tangent, you are actually finding the slope of the radius. As it travels around the unit circle. This is the key. So if I bring the unit circle here into view, you started first looking at a value of 0, and the ordered pair here was 1, 0. And when you calculated y divided by x, that was 0 divided by 1, which equals 0. And if I actually literally look at the radius here, that is truly a slope of 0. It's like you're walking on flat ground. Now in your chart from the previous night's homework, your first value that you possibly considered here was pi over 6, and you found that to be approximately a positive 0.58. So it's kind of hard to show like a rotating radius, but literally imagine we took this radius length right here, and we have now rotated, and its position is now here. Slightly steeper, right? So a positive 0.58 is reasonable. When we got to 45 degrees, or pi divided by 4, tangent here, or the slope, is a slope of 1, a positive 1. Then when we arrive here at pi divided by 3, or a 60-degree angle, you found the tangent, or the change in y divided by change in x, to be a positive 1.73. So as we're moving from our original starting location here at a slope of 0, a flat horizontal line, we see these values gradually increasing, 0.58, 1, positive 1.73, and then we arrive here at our special value of 0, 1, which happens at pi divided by 2, or 90 degrees. You are going to need a highlighter, not just, some of you may have already grabbed some colors, colors from the color box, but in a moment you are going to need an actual highlighter. So if you don't have a highlighter, yellow or your favorite color, I'm going to use yellow. Please pause, press the space bar, grab a highlighter. Let's consider what happened when you calculated the slope here. So when I found change in y divided by change in x, that's going to be 1 divided by 0. And we are all awesome math students, algebra students, and we know that we can't divide by 0. That is an undefined slope. Which makes sense because if I get my highlighter out here, if I consider the slope of this vertical line, back in 9th, 8th, 9th grade, we know that a slope of a vertical line is undefined. Can't do it. So I want to make this super obvious to myself. Vertical line, no good, undefined slope. Now as you continued around the unit, a circle in your table, you notice that these became negative, and so on. So before we keep going, let's focus on the first quadrant. So technically I could keep filling in these numerical values all the way around, but let's see if we can generalize a little bit more. So let me go back over to my skinny pen so I can write a little more detailed. Alright, so if you notice, the title of this blank space here is Exploring Tangent's Journey Around the Unit Circle. So when we started at 0, like we just commented before, we're noticing that the rate of change here is progressively getting steeper and steeper and steeper until it becomes undefined. So when I travel from 0 to here, I'm noticing this increase. But it's going to be literally impossible for me to plot every single ordered pair in this quadrant. There's literally an infinite number of points from here to here. So I know that the slope here is 0 and it's getting bigger. But how big? How big does it get as it approaches pi over 2? Well, let's see if we can generalize a little bit. So as we're approaching this asymptote, we're asking ourselves, can I consider in general what's happening with this rate of change? So let me consider what happens when I have a positive large y value. I'm going to call it big Y. It's going to be a little less than 1, right? Because when y is 1, x is 0. So maybe I'm just going to pick maybe like positive 0.9. That's a decently big y value leading up to pi over 2. And when I pick a positive 0.9, I'm literally saying the vertical distance is 0.9. And if I'm up here for a y value, that x value is going to be super tiny, right? If my vertical distance is 0.9, I'm getting close over here. So super, super small positive x value. So I'm going to put positive small x. And I'm just going to pick a random one because we're just kind of trying to generalize what's happening as it gets super close to this undefined value. So I'm going to pick 0.00, I'm going to do 4 zeros, 0.00004. Why not? So take a second, please take out your calculator, and I am looking for what is 0.9 divided by 0.00004. And when you do that in your calculator, we get 22,000 500. That is huge. So in general, when as I get close to this undefined value, and I'm taking a large y value and dividing it by a super small x value, that output is getting huge. Huge, huge, huge. Does anybody remember how I say in math, like huge is really not a math word, right? Getting huge infinitely. Infinitely far. Infinitely big. And we would say equals, or heading towards. So I'm going to make that an arrow. I meant to move this over a little bit. Remember, this was just like an example we picked. So as I get close to this value, and I am taking a large y and dividing by a very small x, that is heading towards positive infinity. And we can reason that out, because we kind of brainstormed what a change in y over change in x close to this would be. And when we looked at 0.9, positive 0.9 divided by a positive 0.000004, right? Because x is positive and y is positive in quadrant 1. Look how big of a number that was, 22,500. And so these tangents, as I approach this value, are going to get infinitely large towards positive infinity. So now we pass that undefined value, and now we're like right here, directly to the left of it. Let's see if we can reason out again what's going to happen. So if I'm right about here, consider what that y value is going to be. That y length is, again, big. So I'm going to put y divided by x is going to be, again, a big Y. So positive big Y, because even though I'm in the second quadrant, my Y value here is still positive, correct? If I'm on the x-axis, I go up, so positive Y. But now, if I'm in this location right about here, notice what happens to the x value. That x value is no longer positive. It's negative. So we have a positive large Y divided by a negative small x. We can literally imagine this example again, but instead of dividing by a positive 0.00004, now I'm dividing by a negative 0.00004. So this would be negative 22,500. If I want to generalize where these values are headed, how do we say that to the left of pi over 2, values are getting more and more negative forever and ever and ever? We say negative infinity. Again, this is an arrow. So as I choose large y's and super small x's, those values are headed towards negative infinity forever. Let's continue our journey around the circle. And again, from in your homework last night, you did the tangents for all of the nice values from 0 to pi. So you could actually fill out the tangents for these three values, but I'll leave that up to you. So we're heading here, and we're getting progressively less steep, right? If I look at these, the steepness of these radii, less steep, and then I get to this special value of negative 1, 0. So once again, let's look at change in y divided by change in x. That is going to be 0 divided by negative 1, which is 0. And again, I expect to see that, because if I literally ask myself, if I was back in 9th grade and I showed you a horizontal line, you would tell me the slope is 0. So we've headed from negative infinity to 0. Let's keep going. Traveling around the unit circle, we make our way to our next key value at 0, negative 1, which is happening at 3 pi divided by 2. Let's see what happens here. So change in y divided by change in x is now going to be negative 1 divided by 0, which is no good. Undefined. So once again, let's take our highlighter and really make that stand out to ourselves, right? Here, I have once again hit a vertical slope at 0, 1, and we can't have that. It's undefined. But what happens when I get super close to it? Right? I mean, it's much more obvious. When I'm leaving 0, it's going to get gradually, like if I were to draw a radius right there, that's not very steep. So that's going to be pretty close to 0. Getting more steep, larger and larger. But what happens like if I'm right here? So let's reason that out. Change in y divided by change in x. Now I have to realize that my y values are now going to be negative because going down is negative. So that's going to be a negative big Y divided by a negative super small x. So for example, if I was trying to consider the tangent or the rate of change happening at that point right there, literally think about what you just wrote down when you wrote negative big Y and negative small x. We're literally describing that to get from 0, 0 to this ordered pair, you would go left only a little bit, right? The negative small x. And you'd go down a big Y value compared to that super small x. So that, again, that's what we mean by negative big Y divided by negative small x. Well, reasoning on our case that we worked out up here, negative divided by negative is a positive, and that's going to be a huge number. So how do we say getting infinitely big as you approach that undefined value? Positive infinity. We are now passing across our undefined value at 3 pi over 2. And one more time, let's consider what happens right after you pass it. Like, let's say right there, super close. Change in y divided by change in x. Let's see if you can figure out on your own, are we dealing with a negative or positive, big or small y? Those are all the possibilities, right? And then is it a negative, positive, small, or big x? If I'm talking about right there. If someone wants to press pause so you can talk about it for a second, that would be cool too. Otherwise, take a shot. You're doing it in pencil, so if it needs to change, no worries. So I'm hoping the consensus is, drum roll please, a negative big Y and a positive small x. Because to get to this little ordered pair that's super close to the right of that undefined value, you would go right just a little bit, super small, just a little bit to the right, and then that's positive, right? So positive small x value, and then a very big negative y value to get there. So a negative big y value divided by a super small x value is going to approach what? Negative divided by positive is negative, and again, it's going to be huge. So it's going to be approaching negative infinity. And for emphasis, one more time, the reason why it's negative infinity is because you are going to get infinitely close to that undefined value. There are an infinite number of points as you get close to that undefined point. Alright, so we are continuing our rotation here. Past our undefined value, we know that those values are going to get infinitely close to negative infinity. And as we continue back towards the start of our unit circle at 0, our tangent values, I'm trying to decide where I want to put my arrow, our tangent values are returning home, so to speak, and heading back towards 0. So we leave negative infinity. Very, very steep negative values, not so steep, still negative, but not so steep, not so steep, not so steep, until we arrive back at 0. Let's now see what that whole journey will look like when we now graph from 0 to 2 pi. So that's what this space off to the right is meant for. So let's set it up. 8 is going to come out looking so cool. So we're starting at 0, and we're going to 2 pi. That's not straight. It's going to drive me crazy. So you have an extra second to get that set up while I see if I can make myself happy with what this looks like. Alright, that's better. So 0 to 2 pi. Cut it in half. That's pi. Cut it in half again. Pi over 2. 3 pi over 2. Now our trip around the unit circle has actually gotten us all the information we possibly could need to now complete our graph. Check it out. Let's start at 0. What is tangent of 0? Y divided by x, 0 divided by 1 is 0. So our graph will start at 0. Tangent starts at 0. This highlighted section of the graph is jumping out at me. So let's actually address that first. If a value is undefined and we can't be that value ever, there was this really cool word in Algebra 2 that started with an A, where it represented a value that you could infinitely approach but never be. Infinitely approach but never cross. And that word was asymptote. A-S-Y-M-P-T-O-T-E. So that means we are going to have an asymptote at pi over 2 and another one at 3 pi over 2. To make them stand out in my brain, I usually actually put a little X mark on both of these. And these are dashed lines. Now that we have our asymptotes on the graph, let's go back to graphing the rest. So we agreed that we start at 0, and now we are literally going to retrace our steps. As x increases, as our x values increase, we're coming around the circle, And we have already discovered that as I approach this asymptote, as I get close to it, where are the y values, or where is tangent going? As we leave 0 and head towards pi over 2, tangent is approaching positive infinity. We represent that as follows. The graph of tangent is approaching positive infinity. So as tangent approaches pi over 2, heads positive forever and ever, but will never cross pi over 2. As we travel around the unit circle, we pass pi over 2, and what happened? As soon as we crossed over pi over 2, right after it, notice where tangent goes. Tangent is at negative infinity and approaches 0. Let me say that again. Right after pi over 2, tangent is coming from negative infinity to 0. So when I come over here, I am now literally getting infinitely close to pi over 2 in the negative direction. So my tangent values are coming from negative infinity to 0 at pi. Should have labeled that before, sorry. So at pi, we're at 0. So negative infinity to 0. What happens after 0? Well, once we get into quadrant 3, we're dealing with negative divided by a negative, which is positive. So check it out. Right after pi, we are now switching back into positive tangent values. And where is tangent headed? Tangent is headed towards positive infinity. It's going to get infinitely close to the asymptote at 3 pi over 2, but never cross because there tangent is undefined. Right after we pass 3 pi over 2, the tangent values are getting infinitely negative and approaching, let's see, infinitely negative and then coming back to 0 at 2 pi. We have successfully graphed tangent. Let's talk about some characteristics. Amplitude, up till this point when we were talking about sine and cosine, was half the height of the wave, but we definitely don't have a wave here. This graph is going to be approaching negative infinity, positive infinity forever and ever in both directions when we're talking about our y values, so the amplitude for tangent is undefined. To find the period, we need to ask ourselves, how long does it take for what we're seeing on this graph to repeat itself? And when I look, we only graphed 0 to 2 pi. Watch, you don't have to draw this in because I'm going to switch colors. So unless you're able to switch colors, I don't want you to draw this because technically this was 0 to 2 pi. But this does repeat. This one repeats here. This goes here. So if you ask yourself, where's one of those, we actually can see it right here in the middle. So if you have your second color and you want to make a note, I'm writing this in green. From here to here, it shows us that our period is how large. Well, to get from pi over 2 to 3 pi over 2, that is a distance of pi. So the period of tangent is pi. Unlike cosine and sine was 2 pi, tangent is pi. Let's talk domain. Our domain is going to be all real numbers except. Let's see if we can figure out how to talk about where x cannot be. Well, think back to the very first day we did characteristics. We always asked ourselves, where does it happen first? So the very first x value that cannot be happens at pi over 2. Plus, how long till the next one? Well, from here to here is pi over 2, pi over 2. So a distance of pi gets me to the very next one. So we can generalize that by saying plus n pi. Where n is any integer multiple. So what we're basically saying is I'm just going to put i.e. in other words. Plus or minus pi over 2 is no good. Like, this keeps going over here. So negative pi over 2 would also be no good. When you add pi, that's 3 pi over 2. So couldn't be 3 pi over 2. Add another distance of pi. That would actually be plus or minus 5 pi over 2. So it does have kind of a cool pattern where it's all of the odd multiples of pi over 2, which makes sense because the even multiples of pi over 2, right, like 2 pi over 2 is pi, it's 0 there. 4 pi over 2, that's 2 pi. So whichever way it helps you to think about it. Last but not least, our range goes from negative infinity to positive infinity. So that is all real numbers, or you could write negative infinity to infinity. Cotangent is pretty cool because it's very much connected to tangent. So cotangent will be our first reciprocal function. What's nice is that I know on my screen you can only see cotangent, but you have the ability to see what you just did for tangent. And you're going to be surprised how quick this goes now that you have some familiarity with what we've discussed so far. So for cotangent, we're now talking, instead of y divided by x, we're saying x divided by y, which is the same thing as saying 1 divided by tangent of theta. So let's see what happens. Let's start at our starting point, 1, 0. And now x divided by y is going to equal what when you're there? Well, x is 1 divided by 0. Whoa, undefined. We already know that's going to be an asymptote, so we might as well write it right now. Grab your highlighter, really make that stand out. Let's start traveling around the unit circle. So right after this asymptote, now we have to ask ourselves, like, if I'm right here, what happens? Well, now we're talking x over y. So this is now going to be a large x value, right? If I'm going from here to right there, that's going to be a big X divided by a super small y, right? I mean, look how tiny that is. Divided by a positive small y. And we already know that that is going to head towards positive infinity. Continuing our journey, let's see what happens at our next key point at 0, 1, which is at pi over 2. So here, x divided by y is 0 divided by 1, which is 0. So we're here at an asymptote where the values are, as we are approaching 0, the values are infinitely approaching positive infinity. headed towards 0. As we leave 0, these will all be negative slopes. Let's leave some space because we know we're going to do some writing here. So let's see what happens right here. This is going to be at pi. Our ordered pair is -1, 0. Go ahead and find the cotangent there on your own and we'll see if we match. So here, x divided by y will be -1 divided by 0. Uh-oh, can't do it. Undefined yet again. Which we probably kind of expected if that happened over here. But so we know there's going to be an asymptote there. And I want to highlight that, make it stand out. Grab your highlighter. So we're going to have another asymptote at pi, vertical asymptote at pi. But once again, because we're getting so good at it, let's see if we can figure out what happens before I get to that asymptote. What happens when I get super close? Like, let's say right here. Super, super, super close. Well, that's going to be a large negative x value. So a negative, oops, that's too thick. A negative big x value divided by, so let's say I go this far, and it's going to be up a super small y value. So dividing by a positive small y, we know that that's going to head towards negative divided by positive is negative infinity. Right after that asymptote, what would be right here? Remember, I'm not picking that point exactly. I'm trying to represent all of these little points that get infinitely close, but don't touch pi. So that's going to be again, a big negative x value. But this time, instead of going up a little bit, you're going to go down a little bit. So what does that mean about your small y value? Is it going to be positive or negative? I'm hoping we're all saying negative, and I would agree with you. So negative small y. Negative divided by negative is a positive. So those negative big x's divided by negative small y's will result in approaching positive infinity. We continue our travels to our next key value, which is here. Our ordered pair there is 0, -1. Happens at 3 pi over 2. Let's do it. Go ahead and find the cotangent at that ordered pair. X divided by y. And we get 0 divided by -1, which is 0. So we're leaving 0, which means x divided by y is going to start off pretty small and start to get larger. Let's reason out how large. Let's say I'm getting super close to 2 pi, but not quite there yet on the unit circle. My cotangent is going to be a large x measurement, so a positive big x divided by, down a little bit, a negative small y. Those values will approach positive divided by negative is negative. So approach negative infinity, forever, never, never, because they can't cross the asymptote. Very good. Let's see what this graph will look like. So your space here to the right is intended for cotangent. and we're going to go once more 0 to 2 pi. Cut that in half at pi, half again. Where are our asymptotes? So I'm going to X those out first. Now I have an asymptote at 0. Can't be here. Make that a little skinnier. And where else? So we had our first asymptote at 0, and then my next one at pi. And if I look at the connection, you can see it a little easier than I could show it on the screen, but if you look at tangent, the zeros, the x-intercepts of tangent, have now become the asymptotes of cotangent, which makes sense because here, if I'm at 0, 0 divided by 1 got me that coordinate right there. So when I take the reciprocal of that value, it becomes 1 divided by 0. So each of these x-intercepts, when we now graph cotangent, become the asymptotes. The x-intercepts of tangent become the asymptotes of cotangent. Let's begin our journey around the unit circle. Put all that hard work to use. So let's see what happens. I am undefined at 0. We've established that with our asymptote. Our values are coming from positive infinity, where they're getting infinitely large but never going to cross. And as we approach pi over 2, cotangent approaches 0. And cotangent is positive in quadrant 1, which makes sense. Positive divided by positive. Notice as soon as we pass pi over 2 into quadrant 2, now we're negative because that will be a negative x divided by a positive y. And notice the graph flips over the x-axis into negative values. And we're heading from 0 towards negative infinity as we approach pi. So we'll get infinitely close to pi, never cross, with the cotangent values getting infinitely large in the negative direction. Cross over the asymptote. Our cotangent values are infinitely large. Once more, see if I can get it to fit on the same screen. Once more, approaching where? At 3 pi over 2, we're back at 0. So approaching 0, notice, see, in positive infinity, approaching 0. And then finishing it up becomes negative again, heading towards negative infinity. And we have graphed 0 to 2 pi. The only other piece for us to discuss that you'll see in textbooks and we will require in class is our alternating ones and negative ones. Those aren't too bad at all. Let me show you where they are. You actually know where they are, we just haven't graphed them yet. So nice things happen at 45-degree angles, right? So if I were to add pi over 4 and 3 pi over 4 to my scale, which is halfway between 0 and pi over 2, and then again halfway between pi over 2 and pi, notice the tangent of 45 degrees, or the tangent of pi over 4, is 1. So if I put a positive 1 right here, it doesn't have to line up exact. And in like fashion, if you were to have copied your other table values over, the tangent of, I actually don't want to add that to my picture, the tangent of 3 pi over 4 is -1. So those are considered nice points that we can plot, so we will plot them. And they alternate because they're called alternating because they do alternate, right? So here's +1, and then it was at -1. The next nice value would be right here at 1, -1 right there. And that'll come with practice, but it's important we get them in the notes. Same thing with cotangent. So here's 1, -1. Just going to add them in. And I'm totally cool with you adding them in after the fact. That's fine. It's an approximation. We are officially done graphing tangent and cotangent. Let's just finish our characteristics here. Just like with tangent, the amplitude is undefined. Period, once again, let's see. We technically graphed 0 to 2 pi just because we always have as our initial look, made one full trip around the unit circle. But if I notice, this graph repeats after pi. So just like tangents, period is pi, so is cotangents. Domain, all real numbers, x not equal to. With cotangent, it technically starts at 0. So if you wanted to put 0, you could, plus multiples of pi. And our range is all real numbers. Let's now finish up our reciprocal functions looking at cosecant and secant. So with cosecant, if you notice, I have actually provided you the graph of sine because it'll help us to visualize what's going to happen here. So just keep in mind, recall that cosecant is 1 divided by the sine of x, the reciprocal function for sine. So first things first, we know what's going to happen at these guys right here. So at 0, what is 0 for sine will become the asymptotes of cosecant, because it'll become 1 divided by 0 or -1 divided by 0, which is no good. So everywhere where we see the sine function cross the x-axis, those are now going to be asymptotes. So now we already know where those guys are going to be. Let's just pick a value and explore what happens. Let's talk about pi over 2. I need my skinny marker. Let's talk about pi over 2 first. For a reason, sine of pi over 2 is, if we visualize our unit circle, sine of 90 degrees. So imagine that ordered pair that's way up there at 90 degrees, 0, 1. The y value is 1. So sine of pi over 2 is 1. Well, cosecant of pi over 2 is saying 1 divided by that value, which is still going to be 1. It's going to be the same. So for the start of cosecant, that point right there is actually going to be part of our new graph. What if we look at pi over 4? 45 degrees. Sine of pi over 4. We know 45 degrees is really nice. That's root 2 over 2 comma root 2 over 2. Root 2 over 2, which is the y value and the x value, but the y value is approximately 0.7, which, if I kind of reason that out, that kind of makes sense, that's 0.7 right there on my scale. What happens when we consider the cosecant of that same value? Cosecant of pi over 4 is going to be 1 divided by that value. So let's just know that already, that it's 0.7, 1 divided by 0.7. And if you have your calculator out, if you could grab it, that would be great. What is 1 divided by 0.7? 1 divided by 0.7 is approximately 1.41. So I guess these should both be like wavy equal signs. It's not exact. Check that out. So for cosecant, this ordered pair gets sent up here. Like if this is 1, 1.4 would be up here approximately. And that's actually going to happen with all of these. All of these points get, I almost kind of want to use the word reflected, up. So the 1, -1, these ones, where the y value is 1, those become our starting points. And this is what happens. So we can actually technically use the sine wave to really build cosecant. Let's now, though, ditch the sine wave and see what it looks like all by itself. So let's get rid of sine. We're going to go 0 to 2 pi, cut it in half, cut it in half again. Now I really want you to visualize, let's decide where the asymptotes are first. If I were to ask you to draw sine right now, don't do it because we're not going to, but if I did ask you to, you would start at 0. Well, cosecant, anywhere where sine was 0, cosecant has an asymptote. So I know that this is going to be an asymptote. So let's start here, come up here, that's okay. But then I would come back down to 0, no good. The 0 that used to be at pi is now an asymptote. I would come down low, that's fine, and then I'd come back to 0, no good, that's an asymptote. One and -1 are important because those values are still there, right? Notice how it's shared, but now we're going up, up. I kind of made that a little flatter than I wanted. It's definitely a curve. It's a little better. And then alternating. Don't put it over here. It's not over there, right? Look, here the sine wave comes up, so that part of cosecant is reflected upwards up here. And then sine goes down here. So I come over here. That was not so good how I drew that because it almost looked like I was going to cross the asymptote. Can't cross those asymptotes. Cosecant is complete. let's discuss characteristics. You can still see the graph, but mine's going to be off a little bit when I come down here to the box. Amplitude, once more, is undefined. Now for this pattern to continue, if you were to put this into your calculator, or actually just look right here, notice up and then opens down, and then it repeats. It opens up and then it opens down. So the period here, the distance until it repeats, is 0 to 2 pi. So our period is 2 pi. Our domain is all real numbers. And if we look at the locations of the asymptotes, they happen where? I'm hoping we're all saying intervals of pi, and I agree with you. So all real numbers, x cannot equal multiples of pi. Now the range, unlike tangent, is definitely not all real numbers, because check out this giant gap right here in the middle. Our a value is going to be what influences our range, a and d, but that comes later. So when I'm looking at this one, if I were to ask you the range, I'd hope you would tell me negative infinity, which definitely does not get a bracket. I'm just playing. So range, negative infinity up to -1. I can be -1, so it gets a bracket. Union, got to jump this big gap here in the middle. Pick back up at 1, which gets a bracket. Heads to positive infinity forever and ever and ever. So for right now, I am just going to copy down exactly what we wrote. Have in the back of your mind that a, if we have a change in a value, that's going to affect the range. If we have a and d together, that will also affect the range. But we'll be learning that tomorrow. For now, we'll stick with our parent function. Cosecant is all done. Secant works literally the exact same way. So here, let's just make a note. We're talking 1 divided by cosine of x. 1 is going to be fine. But everywhere cosine is 0, that's going to be no good. That will be an asymptote. For cosine, wherever cosine is 0, that is going to be an asymptote for secant. And now, we're about 30 seconds away from being done with this graph, because I have this concept of how the reciprocal function kind of reflects these values up. So from starting here at 1, it's going to go towards positive infinity forever and ever. Down here, -1 will be shared. You kind of think if we did graph cosine and secant on the same graph. So -1 stays, and it's going to open down, getting infinitely close to those asymptotes but not crossing. 1 is shared, or stays, however you like to see it. Opens up. -1 is there, down. So now let's pull it off of that starting point where we still have cosine. Now let's just see what secant would look like all by itself. Zero to 2 pi. Cut it in half. Cut it in half again. Once again, you can visualize cosine as you're graphing. So, for example, cosine starts at 1, 1 is fine. But as I travel, I'm about to approach 0, and that's a reminder to me, oh, no good, have to go in there and get in our asymptotes. because the zeros of cosine become the asymptotes of secant. So as it approaches 0, that's not okay. This will be fine, comes low, comes back up. It would have been a 0 here for cosine, which is no bueno for secant. And so it was going to come down, can't go there. Comes down, that's fine, comes back up, can't be here, and then comes back up. So now we're ready to finish generalizing our sketch. So cosine would have come down, secant's going to go up. It's going to come down here. I always plot the ones and negative ones first. If this branch was opening up, I know that this one is definitely going to open down. And then, again, our 1, approaching infinitely close, but never touching. Now, just like cosine goes on forever and ever and ever and ever and ever, these also continue forever and ever. But we are just highlighting exactly what 0 to 2 pi looks like. Let's finish with our characteristics. We're done graphing secant. Amplitude is undefined. Period. So let's see, how long does it take to repeat? Once again, the repeat starts after 2 pi, so it's going to be 0 to 2 pi, so period is 2 pi. Domain, all real numbers, x not equal to. Our very first asymptote is at pi over 2, and it takes pi for the next one to show up. So pi over 2 plus or minus pi n. And if it helps to kind of give yourself an example, that would be plus or minus pi over 2, plus or minus, if you added a full pi to that, 3 pi over 2, and then another full pi to that would be 5 pi over 2, and so on. So like the odd multiples of pi. Range, once again, is affected by a. If d was involved, a and d. In this case, a is 1. So notice, -1 and 1, big gap in the middle. That's no good. So our range, our y values, go from -infinity up to -1. It can be -1, so -1 gets a bracket. Union, bracket, 1 to infinity. We have officially finished really understanding where all of our tangent and reciprocal functions come from. And it's definitely food for thought. So it might take a little bit of practice to kind of really own that reasoning, but that's what tonight's homework is all about. So please jot down any questions, and I'm excited to see how your tries at repeating the reasoning goes. Let me know. Have a great day, everybody.